One way to represent the forces acting on an object is what we call a force diagram. A force diagram is basically a picture of the force vectors that are acting on that object. So at the end of this lesson, you should be able to define a vector quantity, and you should be able to draw force diagrams. So these are your main focus questions for your notes. Remember that a force is simply a push or a pull acting on an object. Forces are what we call vector quantities. And you may have heard this term before.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
So let's distinguish a few things. Some quantities that we refer to don't have a direction associated with them. These are called scalar quantities. These quantities only have a magnitude that tells us how large or small the quantity is. Things like your age. You can only travel in one direction in time, so it's not necessary to specify that you are getting older. Speed is another example. We can say that we are traveling 35 meters per second on the way to Manhattan, but we don't need to say that we're going north. A vector, on the other hand, is a quantity that has direction and magnitude. Forces are the ones we're talking about right now. When you push something, you are applying some size of force, which is the magnitude, but you are also applying that force in some direction. The direction is an important part of that description. It makes a big difference if you're pushing to the left or to the right. Vectors are represented by arrows. The direction the arrow points is the direction of the quantity, in this case, the force. So the first arrow there indicates the force is acting to the right. The second vector shows the force acting to the left. The length of the arrow indicates the magnitude. So a longer arrow means that the force is larger. This 20 Newton force vector will be drawn twice as long as a 10 Newton force vector. Force diagrams use vectors to represent the forces. These are just visual pictures of the forces that are acting on the object at any given time. To draw a force diagram, the first thing we need to do is identify the system. A system in science is simply whatever we're talking about. You can include as many things in the system as you want, but as a general rule, the fewer things, the better. In this picture, we have a flamingo standing in the ocean. So let's just decide right now that we're going to describe the forces acting on that flamingo. This makes the bird our system. Now that we have identified our system, we want to identify the forces that are acting on it. So first off, we are on Earth. This means we have gravity. What else do we have? Why isn't the bird falling towards the center of the Earth? There's a surface pushing up on it, keeping it in balance. Do you remember what that force is called? Anytime we have our system sitting on a surface, we have what's called a normal force. Can you think of any other forces that might be acting on this bird? That water looks pretty calm, so I think we can ignore any force that might be coming from there. It also doesn't really look like there's any wind to speak of. So let's just go with gravity and normal. Forces are vectors, so that means we need to figure out which direction those forces are acting. So we have gravity and normal as the forces acting on our system. Gravity will pull the flamingo down. Always. If there is ever a situation where that will not be true, it will be indicated in the problem. Now our flamingo looks to be standing on a fairly level surface. The normal force, remember, acts at a right angle to the surface. So if our surface is level, the normal force will be acting straight up. Now, to draw our force diagram, we are going to take our system and shrink it down to a little box. This little box is just simply a way to represent our system without having to deal with any complicated angles, legs, feathers, things like that. You will always draw your force diagram from a box. If there's a picture of the problem that you are working on, do not draw your force diagram on the picture, and don't try and draw the flamingo as your force diagram. Always draw your vectors from the box that represents your system. Now we are going to draw our vectors onto the box that we will be using to represent our system. The force of gravity is going to point down. We always start the vector on the box and point in the direction the force is acting. So our gravity vector is going to be an arrow that points down out of the bottom of the box. The normal force vector will start at the top of the box and point in the up direction. Now the last step is to label each vector with a force it represents. Remember from the types of forces lesson that gravity is designated with an FG and normal is FN. So this is our complete force diagram. We have a vector representing gravity pulling down, and we have a vector representing the normal force pushing up. So pause the video and take a few minutes to sketch out the force diagrams for these four situations. So we have a girl suspended motionless from the monkey bars. Now, typically when somebody hangs from monkey bars, they're hanging with both arms. So in a force diagram, we want to represent every force that is acting on that object. So we can probably say that our girl is the system. There's really not a lot of other things that we could identify as a system in this problem. So the girl is our system, and she is hanging from the monkey bars. So both of her arms are applying a force to her. Now we're hanging, so pretty much any time that we're hanging, we're going to have a tension force. And each one of her arms applies a tension force. So we'll have two arrows coming out of the top to represent both of her arms. And then of course we have gravity pulling her down. So if she lets go and she doesn't have those forces acting on her arms anymore, gravity is going to pull her all the way down. What if we have a sled sliding across an icy pond? In this class, unless otherwise stated, ice is going to be frictionless. So there's no friction on our ice. In reality, that's not quite true, but for our situations, that's what we can say. So we have a sled going across on our icy pond. If there's no friction and nothing making our sled go, there's no other forces that are pushing it. So gravity is going to pull down, and it's on a surface. And again, if it doesn't specify, we can say that our surface is level. So we're going to draw our gravity pulling down and our normal pushing straight up. Now what happens if our sled slides onto the grass? Now we're going to have friction. So we don't have anything pushing that sled, but it's going to hit the grass. And so we're going to have some kind of friction slowing it down. Now, since it doesn't specify, we can draw our friction force in either direction. So remember, friction acts opposite the motion. So think about that. Which direction would my sled be going? So I pictured my sled moving to the right. So I drew my friction to the left. If you were to imagine your sled going to the left, then you would draw your friction going to the right. And either one of those are correct because it didn't say one way or the other. So now you get off your sled and you start to pull it across the grass. Okay, now we have an applied force. So I am pulling on the sled. That's going to be the applied force pulling it to the right. We're still on grass, so we're going to have friction going to the left. We're still on earth, so gravity is going to point down. And we're still on a level surface, so our normal is going to point up. How are we? Can you define a vector quantity? And can you draw force diagrams? Make sure in your notes you have these questions noted.